and this strand is on measurement. The other audiovisual that we have created before, the one before this, had questions 1 and 2. We will therefore continue the presentation by taking a look at question 3. The back of a truck is in the shape of a rectangular prism. Boxes shaped like cubes will be loaded into the back of the truck. The dimensions of the back of the truck, which is not drawn to scale, that is, the back of the truck is not drawn to scale. The dimensions are shown right there. Use 2 numbers from the list to complete the sentence below so that the statement is true. So here we have the list and the statement that we are attempting to cause to be true. For it to be true, we will make use of the boxes, which are cubes, and the edge of each cube is given right here, and with the edge of the cube we have numbers which will represent the number of cubes that are able to be loaded in the back of the truck. So let us say that we are going to cause this statement to be true. If the edge of the box is 2 meters, then the back of the truck can hold 25 boxes. That's how the statement is to be completed, but the one that I made just now is not correct. We'll take a look eventually at how we may make the relevant calculations that will cause the statement to be true. But before we do that, we need to construct or reconstruct the back of the truck. So take note of the dimensions of the back of the truck that we have here, which of course we were told not drawn to scale. So take note of the dimensions of the back of the truck. We will construct a cuboid by making use of those exact dimensions. So the dimensions that we have are 9, 4, and 6. And we are urged at this moment to take note of those dimensions because we are going to reconstruct the back of the truck so that we can make our calculation. And we are not merely making a calculation, but we are causing our calculation to be practical. So it is the practical application of the calculation that we are driving at, and we will reconstruct the back of the truck in order that we may achieve our goal. We know the dimensions of the back of the truck. Let us construct it by making use of a cube with edge 1 meter. We are choosing 1 meter because the dimensions of the back of the truck are in meters. So that transition or that calculation or the arrangement that we are making is going to be made easy because the dimensions of the back of the truck are in meters. So we are going to use the cube that we have right here, whose dimension is 1 meter. Of course, a cube of edge 1 meter means that the length is 1 meter, the width is 1 meter, and the height is also 1 meter. The longest dimension is 9 meters. With the length of each edge equal 1 meter, it means that 9 cubes are required to form that edge. So the first dimension is 9 meters. That is the one that we are attempting to create at the moment. 9 meters. The edge of the cube is 1 meter, so we need 9 of those. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the first dimension of the truck. The horizontal dimension, if we can remember, and if you don't, we have that on the screen right there. So the horizontal dimension is 4 meters. We will therefore have 4 of those groups going horizontally. And of course the first pack is there already. So in the other dimension, in the other direction, we have 4 meters. That means we have 4 cubes going in that direction. 4 cubes of edge 1 meter each. And we have the first pack already. So we are going now in the horizontal direction. Then we will finish up by going in the vertical direction. But before we do that, we will insert the dimensions that we have there. 9 meters, 4 meters. Finally, the vertical dimension is 6 meters. We therefore need 6 of the new packs going vertically. So 6 of the packs going vertically, 1 pack for each meter, because the cube is of edge 1 meter and we have 6 meters, so we need 6 of them. Of course, the first pack is there already, so we just need to include the others. 1, 2, 3, 4, 5, 6. Let us also insert that vertical dimension. So we have included or inserted the other dimensions, 9 meters and 4 meters. So we will just include the 6 meter dimension. Let us now draw a simpler version of the back of the truck. So we will use the arrangement that we have there, created by the cubes of edge 1 meter, and we will use that arrangement to draw a version of the back of the truck that is more true to life than the one that we had there. So we're going to put in all of those lines. The back of the truck is in the shape of a cuboid or a rectangular prism. There we have it. That is your cuboid, and the cuboid represents the back of the truck. And here we are again, reflecting on the statement of the problem. The back of a truck is in the shape of a rectangular prism or cuboid. Boxes shaped like cubes will be loaded into the back of the truck. The dimensions of the back of the truck, which is not drawn to scale, that is, the back of the truck is not drawn to scale, are shown. And what do we need to do? Use 2 numbers from the list to complete the sentence below so that the statement is true. So that is the statement that we need to be true. Now we will take an approach which is one that is somewhat logical but might not be practical. So let us go straight ahead and see if we can find the number, because we have the edges here, 1 meter, 2 meters, 3 meters, and we will see how many of these will hold in the back of the truck. And we are going to attempt to do that based on calculations alone, and let's see what will happen. So let us take an approach by only, and we are stressing only in this particular case, considering the volume of the cuboid to be 9 by 6 by 4, which is equal to 216 cubic meters, and the cubes to be 1 by 1 by 1, which will be 1 cubic meter. The other one will be 2, the one with edge 2 meters will be 2 by 2 by 2, which will be 8 cubic meters. And finally we have 3 by 3 by 3 for the cube of edge 3 meters, and that will give us 27 cubic meters. The length of the edge of each box is required to go into the first slot. So the edge of the box is, we need to put that in the first slot. The number of those cubes that can hold in the back of the truck is for the second slot. Let us see how many of the boxes of edge 1 meter will fit, that is, fit in the back of the truck. 1 meter. To find the number of them, we need to divide the volume of the back of the truck by the volume of each box. We need now the number of these boxes of edge 1 meter that will hold in the back of the truck. So let us take the approach that we are dividing the volume of the back of the truck by the volume of each box. Now, instead of writing 216, we are doing it like this for reasons that will be obvious when we take a look at the boxes of other dimensions. So we have the dimension 9 by 6 by 4 to be divided by the dimension, that is the dimension of the truck, and this is the dimension of the box. So here we have 216 to be divided by 1, and any number that is divided by 1 is equal to that same number. Any number divided by 1 is equal to itself. So 216 divided by 1 is equal to 216. The truck can hold 216 boxes with edge equal to 1 meter. And do we have a representation there? Yes, we do. 216 right here. Let us do the same with the box of edge equal to 2 meters. 2 meters will be the edge of the box in this particular case. The number of them will be equal to the volume of the truck divided by the volume of the cube. That's what we imagine, that's what we think, that's what we say. And again, we have this product here because of the dimensions of the back of the truck to be 9 by 6 by 4, and the dimensions of the box will be 2 by 2 by 2. And we are not putting 216 here because if we reduce by a common factor that we can see here, then the calculation can be made to be very much simpler. We see that 2 times 2 is equal to 4. So the 2 times 2 will cancel that 4. So 4 can be cancelled from both numerator and denominator. So take those out. The fraction may be further reduced by a common factor of 2. Because we have 2 into 2 is 1, and surely 2 will divide into 6 also, and that will be 3 times. So we have in the numerator 9 times 3, that's left, that's equal to 27, and only 1 remains in the denominator. Any number divided by 1 is equal to itself. Therefore, the answer is 27. And so far, it looks like our calculation is very organized, constructed, logical, and workable. 27. Now, this might be a shock to us all, but 27 is not correct. And we will see why this is so later on. So later on, we will see why the 27 is not correct. Although the calculation volume by volume gives the correct answer. Well, gives the answer to be 27 in this case. And we will also take a look at the box with dimension 3 meters. And that will finish up the boxes with their respective dimensions. So finish up this section by taking a shot at the box of edge 3 meters. 3 meters will go there. The number of them will be equal to the volume of the truck divided by the volume of the cube. And we know the volume of the truck. But this time, the volume of the cube will be 3 by 3 by 3. And of course, we can capitalize on the fact that we have 3 3's equal to 9. So 3 times 3 is equal to 9. And that can be cancelled from the numerator and denominator. So this 3 times 3 is 9. Will go with that 9. Those may be eliminated from the denominator and the numerator. The fraction may be further reduced by a factor of 3. So there is still a common factor of 3. 3 may go into 3 and 3 may also go into 6. 3 into 3, 1 time, and 3 into 6, 2 times. 2 times 4 is equal to 8. That is what we have here. 2 times 4, that's equal to 8. And in the denominator, we only have 1 remaining. So we have 8 over 1, and any number divided by 1 is equal to that same number. So right there, we will put 8 boxes. The edge of the box is 3 meters. Then the back of the truck can hold 8 boxes, according to the statement that we have there. And we are saying 8 is also not correct. And we will see why this is so later on. A practical approach will clarify everything. So we are going to take a practical approach. First, we took a logical approach, which might appear to be 100% sound, but it is not 100% sound, and we need to go to our practical application. As a matter of fact, Richard James Mathematics Resources believes that a practical application is always necessary when we are required to think critically. So if we are doing critical thinking, a practical approach is the best approach that we can take. So our practical approach is that we will actually load those boxes in the back of the truck and see what happens. And because the back of the truck was constructed by making use of those boxes, then we already know how many of those boxes of edge 1 meter can hold in the back of the truck, because that's how we constructed the back of the truck, by making use of the boxes of edge 1 meter. And in that dimension, which is 9 meters, we have 9 of those boxes in that direction. We then have 4 of those groups of 9. So 4 9s equal 36. So the dimension is 4. So we will have 4 boxes going in the other direction, and we will take the entire group. So let's do that. 1, 2, 3, 4. Just like before. We will not be caught off guard. We will not be caught with 1 foot on the ground, because the way that we constructed the back of this truck was by making use of those cubes of dimension 1 meter, or edge 1 meter. So we know the answer. What we are doing though is warming up for the case when the edge of the cube is either 2 meters or 3 meters. Finally, we have 6 of those groups of 36, which will turn out to be 216. This means that 216 cubes of edge 1 meter may be loaded into the back of the truck. Four, 5, 6. No problem whatsoever. So we are not surprised. We say that 216 boxes of edge 1 meter can fit into the truck, both numerically and physically. So when we did the calculation by dividing 216, which is the volume of the back of the truck, by the volume of the cube, we got 216. And when we load them into the back of the truck, physically, practically, we got 216, which does not come as a surprise to us. If we use the numbers, only 27 boxes of edge 2 meters will fit. And we are saying 27 because when we actually did the calculations a few slides ago, 27 is the number of boxes that we received when we use the cubes of edge 1 meter. So let us say that if we use the numbers only, which is just do the calculation only, as we did before, 27 boxes of edge 2 meters will fit, but it is not practical. By using the numbers only, 27 boxes of edge 2 meters will fit, but that is not practical. There we have the statement of the problem, and I'm not going to be reading through this again, but let us look here where we have, if the edge of the box is whatever, 1, 2 or 3 meters, and then we have the number of boxes that can hold. So use two numbers from the list to complete the sentence below so that the statement is true. So that's your list. We have it right here, and we have the sentence right there. So let's see. We have concluded earlier on by calculations and then by actually fitting the boxes that 216 cubes of edge 1 meter can hold in the back of the truck, which is the back of the truck that we are talking about is of dimension 9 meters by 6 meters by 4 meters. So for the 1 meter box, we have 216, and those two numbers are represented in the list. So we have no discrepancy for the box of edge 1 meter, as each of the dimensions of the truck is divisible by 1. So each dimension of the truck is divisible by 1. So as long as the boxes are of dimensions 1 meter by 1 meter by 1 meter, all of them will fit into the back of the truck exactly. Therefore, if we load them in or we do the calculation alone, then the answer will be the same and the answer will be correct. All of those boxes will therefore fit the dimensions exactly as we said before, because it's just 1 and 1 will go into any whole number and the dimensions are in whole numbers. So that may be done quite easily. Right there we have the two items from the list that cause the statement to be true. And what are those? The 1 meter box, then the back of the truck can hold 216 boxes we have right there. Before taking a look at the number of boxes with edge 2 meters that will fit into the back of the truck, let us take a look at the actual volume of the box of edge 2 meters. What's the actual volume of the box of edge 2 meters? So we are going to begin as usual with our 1 meter edge box. So we have right there our basic cube, the box of edge 1 meter. Its volume is length times width times height. All of the dimensions are equal to 1. Therefore, its volume is 1 times 1 times 1, which is equal to 1 cubic meter. The volume of the cubic box of edge 2 meter is what? 2 times 2 times 2, which is equal to 8 cubic meter. Therefore, one box of edge 2 meter will occupy as much space as 8 boxes of edge 1 meter. There we have the volume of the box of edge 1 meter, which is 1 meter cube or 1 cubic meter, and the one with 2 meter edge, 8 cubic meters. So we need 8 of these boxes to form one of this. So let's go. So we'll put 8 of those 1 cubic meter boxes together, 4 of them. So put in another 4. Right, as I was just afraid that the last box would not be included, but it is. Let us fit our cube of edge 2 meters with those 8 boxes of edge 1 meter. So let us fit the 2 meter box with those 8 boxes. So 8 of those will form one of the 2 meter edge box. So that's the size of our box, and that's the one that we will use in a minute. The boxes of edge 2 meter can fit exactly into the dimensions of 4 meter and 6 meters. This is because 2 is a factor of both 4 and 6, but they cannot fit exactly into the dimension of 9 meters. So as we said before, let me repeat that. This is because 2 is a factor of both 4 and 6. That is why the box of edge 2 meter will fit into the dimension of 4 meter and 6 meter exactly, but it will not fit into the dimension of 9 meter exactly, because 9 is not a multiple of 2. So 4 divided by 2 will give us 2. So 2 of those boxes will fit into this dimension. Six divided by 2 is equal to 3. So 3 of the sets of 2 boxes will fit along that edge. So we have 3 times 2 is equal to 6 boxes in all. So because 2 into 6 will be 3, we will have 3 of this set going in the vertical direction. So the first one is there already. So 2, 3. So we have 3 of them. 2 is not a factor of 9. The boxes will not fit exactly. Take a look at the number of them. Those will not fit exactly because 2 is not a factor of 9. So we have 1, 2, 3, 4 sets. 4 sets of 6 boxes. So 4 times 6 is equal to 24. A total of 24 boxes of edge 2 meters will fit. The option catered for 24 boxes of edge 2 meters. If we take a look at the list that we have there, we will have the 24 boxes mentioned, of course, and we see that the 24 boxes will be for the boxes of edge 2 meters. So we have 2 fit exactly, 3 fit exactly, 4 is fitting right here but not exactly because there is space left over, because 2 does not divide into 9 exactly. If the edge of the box is, we are working with a 2 meter edge at the moment. We just saw that 24 boxes of edge 2 meters will fit into the truck. They do not fit exactly, but the statement of the problem did not require that they fit exactly, only that they fit. Space will be left in the truck, but no other box will be able to fit. Space will be left in the truck, but no other box will be able to fit. So 2 meter boxes of edge 2 meters, and of course we know 24 is also in the list, and the calculation that is based on the practical application gives 24 boxes, so we know that 24 is correct. By rough calculation, for 4 meter divided by 2 meters, which is equal to 2 boxes will fit. For 6 meters divided by 2 meters, which is equal to 3 boxes will fit. For 9 meters divided by 2 is equal to 4, and the remainder of 1. The remainder means insufficient space for an entire box. Using all of the quotients, we have all of the quotients is equal to 2. This one is equal to 3, and this one is equal to 4. So using the quotients, how many times the box will go into that dimension? 2 times here, 3 times there, 4 times there. Multiplying them together, we get 24. Later, we will see how much space in volume will be left. You know, it does not fit exactly. Because it does not fit exactly, then we know that space will be left, and we will take a look at how much space is left over. Right there, we have the 2 items from the list that causes the statement to be true. So the statement is not only true for 1 meter and 216 boxes, it is also true for 2 meters and 24 boxes. Before taking a look at the number of boxes with edge 3 meters that will fit into the back of the truck, let us take a look at the actual volume of the box of edge 3 meters. So we will examine the volume of the box with edge 3 meters. And again, we are using as our atom, our basic building block, the box of edge 1 meter. So we have right there our basic cube, the box of edge 1 meter, and we know its volume. We discussed that before. The volume of the cubic box of edge 3 meters is 3 times 3 times 3, which is equal to 27 cubic meters. Therefore, 1 box of edge 3 meter will occupy as much space as 27 boxes of edge 1 meter. So we need 27 of these boxes to form in volume the box with edge 3 meters. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Let us fit our cube of edge 3 meter with those 27 boxes of edge 1 meter. Fit that right there. That will be our new cube that we will fit into the back of the truck. The boxes of edge 3 meters can fit exactly into the dimensions of 9 and 6 meters. This is because 3 is a factor of both 9 and 6, but they cannot fit exactly into the dimension of 4. 9 divided by 3 is equal to 3. 3 of those boxes will fit along the 9 meter edge and they will fit exactly. Then 6 divided by 3 is equal to 2. 2 of those sets of 3 boxes will fit along that edge, because 2 times 3 is equal to 6. Then we are sure that that will be 6 boxes in all. So for the dimension of 6, we have 3 into 6 is equal to 2. So 2 of those. Not only that 3 is not a factor of 4, we saw practically and we know that only one box of edge 3 meters can fit along the 4 meter edge. So we are saying not only because 3 is not a factor of 4, meaning that if we take a mathematical approach, it is obvious that it will not work, but also that if we attempt to fit the boxes, they will not actually fit. So we will see that because of this smaller space here, we know that another box, or it is impossible for another box of edge 3 meters to be fitted here, because when we put this one right here, only 1 meter remains. Only 6 boxes of edge 3 meters will fit into the truck. We just saw that 6 boxes of edge 3 meters will fit into the truck. They do not fit exactly, but the statement of the problem did not require that they fit exactly, only that they fit. Space will be left in the truck, but no other box will be able to fit. So although we have the list that say 3 meters there, which we put into its slot that is there for it, we have 6 here, and 6 is not in that list. By rough calculation, 9 divided by 3 is equal to 3. So 9 meters divided by 3 meters, which will give us 3, and that will be the number of boxes that will fit in that dimension. And then for 6, we have 6 divided by 3, which is equal to 2. 2 boxes will fit in that dimension. But for 4, only 1, and a remainder of 1. So 4 divided by 3 is equal to 1, and there will be a remainder of 1. The remainder means that we have insufficient space for an entire box. So using all of the quotients, we have the one that goes into 3 times, the next one will go into 2 times, and the other one will go into 1 time, 3 by 2 by 1, and that is equal to 6. Later we will see how much space in volume will be left, so we'll take a look at that also. The information causes the statement to be true, but the number 6 is not in the list. So there is where it fails for the box of edge 3 meters. The number of boxes that can actually hold is not in the list. The boxes of edge 1 meter fit perfectly. There is no space left. And we do not have to labor over this, because we know from 2 previous slides, the one that we use to construct the back of the truck is the one that makes use of those 1 meter boxes, and the one also that we take a look at how many of them will hold in the back of the truck, which we already knew. We have no space left. We know the number of boxes and we know how they fit. We have a lot of experiences from the previous slides. The boxes of edge 2 meter can fit exactly into the dimensions of 4 and 6 as we saw before. However, for the dimension of 9, 1 meter was left over. Fit exactly 2 meters, the size of each edge. For the dimensions of 4 and 6, they fit exactly, but for the dimension of 9, 1 meter is left over. There is therefore cuboidal space left in the back of the truck. What is the volume of that space? What is the volume of that space? Right. We can see that this space is the same dimension here, right there, and the same dimension down here, right there. But this dimension that we have right here is just 2 meters. So 2 meters for the remainder, and the other dimensions will be the same. For the dimensions of the space left over, 9 divided by 2 is equal to 4, and the remainder is 1 meter. The remainder created this space. So it is the remainder that creates the space, and the space has a dimension there of 1 meter. Right there, the leftover, and then the other dimensions, 4 by 6 will be, so 4 meters, 6 meters by 1 meter. So the volume is 1 by 4 by 6, and that is equal to 24 cubic meters. And that 24 cubic meters is very much greater than the volume of the box. The volume of the box is 8 meters cube, or 8 cubic meters. It cannot fit, although the volume of the space is significantly greater than the volume of the cube. The volume of the space being 24 cubic meter and the box being 8 cubic meters still cannot hold, because there is a remainder of only 1 meter. So for that dimension of 1 meter, the 2 meter box will not fit. The boxes of edge 3 meter can fit exactly in the dimensions of 9 meter and 6 meter. However, for the dimension of 4 meter, 1 meter was left over. So that is for the cubes of edge 3 meters. We have established that before, so we know how they may be loaded in the back of the truck. Fit into the dimension of 9 exactly, and fit into the dimension of 6 exactly, not fitting in the dimension of 4 exactly at all. And this volume is very large. Here again, there is a cuboidal space left in the back of the truck. Let's find its volume. So the volume of that cuboidal space, we can see right here that this dimension is the 1 meter that was left over from the 4, and we have 9, and we have 6, or we have 9, we can say 9 here, and then we say 6. Doesn't matter, as long as we realize that the dimension of the space will be caused by the remainder of 1 meter there, and then the other dimensions 9 and 6 will be the same as before. Its volume, which is 54 meters cubed or 54 cubic meters, 1 by 6 by 9, is very much greater than the box 27 cubic meter. Although it is very much greater than the box, again we see that it cannot fit because the thickness of 1 meter cannot accommodate the dimension of the box, which is 3 meters. We will continue this presentation with question number 4. The diagram below represents the outline of a tire on a toy cart. What distance will the cart travel if the tire makes 1 revolution? When making your calculations, use pi to be 22/7. As a matter of fact, since pi is given as 22/7, this is a clue to what we will do, or we are required to do, in order that we may solve the problem. But let's take a look at it again. The diagram below represents the outline of a tire on a cart. What distance will the cart travel if the tire makes 1 revolution? When making your calculations, use pi to be 22/7. The most important point is the statement that we have right there that we are going to highlight. What distance will the cart travel if the tire makes 1 revolution? Before we can make sense of it, we need to know what is 1 revolution or a revolution. Cannot solve the problem if we do not know what a revolution is. Revolution, that's the statement. That is the word in the statement of the problem that we need to pay attention to immediately. When an object traveling in a circular path returns to its point of origin, that is 1 revolution, or we may say it has gone 1 revolution. When an object traveling in a circular path returns to its point of origin, that is 1 revolution, or we may say it has gone through 1 revolution. We will demonstrate what 1 revolution is. So to demonstrate this, we will place 2 identical stars on the same spot on a circle, like the tire on the toy cart. So we will demonstrate 1 revolution, and in order to do that, we will place 2 stars at the same spot. So those 2 stars are at the same spot. When the star returns to where it started, it would have completed 1 revolution. So the star goes all the way around and returns to its place of origin. That is 1 revolution. Let's see. Begins and returns to its point of origin on the circumference of the tire. It would have gone through 1 revolution. Next, we will take a look at the distance associated with it. So we are going to take a look at the distance associated with 1 revolution. So we know what 1 revolution represents. Then we will take a look at the distance associated with that 1 revolution. if we wind a piece of rope around the tire in such a way that it begins and ends at the same point, would it have completed a revolution? That's the question. If we wind a rope like so around the tire like that, would that rope have completed one revolution? Take the rope, begin at that star, go all the way around, and it touches the end or the other end where it started from. Would it have completed one revolution? Yes, it would have completed a revolution. So we are sure that the rope would have completed one revolution, wound around the tire exactly one time. So we will now take a look at the rope, what it will look like when we unwind the rope. So there we are, unwinding the rope. Unwinding the rope. So we see that the rope that we have that was wound around the tire is the same rope that we have extended right there. What distance will the cart travel for one revolution? We see that the length of the rope is the same as the distance around the tire, because what we have done is we have wound the rope around the tire to one revolution. Then we unwind the rope. Therefore, we are sure that the distance of one revolution and the distance of the extended rope will be the same. We see that the length of the rope is the same as the distance around the tire. They are equal. The same rope was wound around the tire. The distance that the cart travels would be the length of the rope. That will be the distance that the cart travels, the length of the rope. And that length of rope is the distance associated with one revolution. So here we have our length of rope. Whatever this distance is, it must be the same distance as when it was wound around the tire. It's the same piece of rope. It's the same length. We are here focusing on the main statement of the problem, which is what distance will the cart travel if the tire makes one revolution? And we saw on the previous slide that the rope wound around the tire and then unwound is the same rope, so the distance that we have here is equal to the distance around the tire. And we already know what we call the distance around a circle. We know what we call the distance around a circle. We need to find the distance associated with one revolution of the tire. We need to find the distance associated with one revolution of the tire. Let us begin with the point where the tire is in contact with the ground. The tire is in contact with the ground right there. Let us begin with the point where the tire is in contact with the ground. When the wheel turns until the point is in contact with the ground again, that is one revolution. So the wheel will turn eventually till the point that is in contact with the ground is again in contact with the ground. Then the wheel would have gone one revolution, and the distance associated with it is the distance of one revolution. The distance traveled will be equal to the length of the unwound rope that we have demonstrated. The distance traveled will be equal to the distance around the circle, which is its circumference. That's the word that we were groping for a long while, and now we are mentioning it. The circumference is the distance around the circle, and that is the distance associated with one revolution, which is the distance that the cart would have traveled if it moves in such a way that the point that is on the ground goes all the way around and returns to be in contact with the ground again. And it is also the distance or the length of the rope that is wound around the tire exactly once. We will make the calculation on the next slide. So here we are, and we are required to make the calculation, and we are emphasizing, re-emphasizing, and over-emphasizing the distance that the car travels for one revolution of the tire. Around it once, that's one revolution. The circumference of the circle is given by C is equal to pi times D, D for diameter. Pi is given to us as 22/7. C, which is the circumference, is equal to pi times the diameter. And pi is given to us as 22/7, and we have the diameter right there, which is the line that goes from one point on the circumference to the other point on the circumference, but it goes through the center of the circle. So it is the straight line segment that goes between 2 points on the circumference of the circle and also passes through the center of the circle. That is the diameter. And pi is given to us as 22/7. D is the diameter of the tire. Now, the problem that we have there has a common factor of 7 in both numerator and the denominator. The fraction is therefore reduced by a common factor of 7. So 7 into 7 is 1 time, and 7 into 28 is 4 times. So 4 is what we have here. So we have 22 times 4, that is equal to 88. And we have 1 times 1, which is equal to 1. So the fraction is reduced to 88/1. Any number divided by 1 is equal to itself. So 88 centimeters will be the circumference of the circle. It will be the length of the rope that is wound around the circle, and it is going to be the length of the rope that was unwound, and it will therefore be the length or the distance traveled by the wheel of the cart when it goes through one revolution. We have calculated the circumference of the circle to be 88 centimeters. That is equal to the length of the rope around the tire. The 88 centimeters is equal to the length of the rope around the tire, because as a matter of fact, that's the circumference of the tire. So it has to be the length of the rope that was wound around the tire. the circumference. Unwind the piece of rope. When we unwind the piece of rope, like we do right there, then this distance will be the length of the rope, and it will be the distance that the car travels in one revolution. The length of the rope is the distance that the cart travels when its tire goes around once, which is one revolution, and that is our distance traveled by the wheel, which is 88 centimeters. The reason for calculating the circumference is that the distance that the cart travels is equal to the distance of one revolution, which is the circumference of the tire. So the reason for calculating the circumference is that the distance that the cart travels is equal to the distance of one revolution, which is the circumference of the tire. So we are at the end of the audiovisual presentation, which is the second part, which is the second strand, which is measurement for the PEP Mock curriculum-based test. So I hope that you would have gathered enough information that if you are required to think somewhat about whatever else you need to do, that this video presentation would have been of some great assistance to you, not only for the solution of the paper, not only for the answers, but for the principles that were discussed, especially for the principles that were discussed. And we imagine that you will be able to apply those principles under other circumstances.